All right, so today we are going to go back to solving some word problems. Now, for the most part, we are going to set these up and then not actually do the solving portion of it. We will discuss how to do the solving, but just to kind of maximize the use of our time, we're not going to actually go through and solve these. A lot of it's just solving on your calculator or using the different methods you're already familiar with. And I really want to just focus on the actual word problem. Okay, so let's start by just reviewing this equation up the top. So this is your formula for either a falling or a thrown object. Okay, so just as a reminder, this negative 16 here, that is the force of gravity. Okay, and this is specifically talking about feet per second squared. That would be different if you were talking about meters or some other unit of measurement. All right, so that's your gravity. This V naught, right, is your initial velocity. So it's your initial velocity. Velocity, remember, speed with direction. So it's essentially how much initial force you're putting on the thing and whether it's going up or down. Okay, and then H naught is your initial height. Okay. All right, so that's the setup that we're going to use for some of these equations. So let's look at the first one. World Diving Championship, they dive from a height of 92 feet with an initial velocity of 5 feet per second. How long do you have to perform the maneuvers before hitting the water? Okay, so we got a couple of things that we need to deal with here. So first of all, let's just think about what is kind of happening in this problem. Okay, so we've got some guy, right? This is my coordinate plane. What's happening is that I've got some guy up here on a diving board, right? There's my guy, right? And he is gonna dive off of this. So he's jumping up and coming back down, okay? So we want to figure out how long does he have before hitting the water. So essentially what we're going to be looking for here is this point, right? I want to know when are we hitting the water. And in terms of what my coordinates are, right, time is my x coordinate. So this guy over here, this is your time, all right? And then this is your height. It's a height by time function. So if I want to know how much time does he have, all right, well, that is going to be your x coordinate, right? So what I'm looking for is I'm looking for the x coordinate of the x-intercept. Okay, so that's the first thing that you want to worry about is what are you actually looking for? All right, so now I'm going to go ahead and set up my equation. So my equation for this guy is going to be h of t. And remember, that's just function notation. It's not h times t. It's just telling you that this is a height function as a function of time, okay? So it's going to be negative 16t squared because it's telling me that I'm using feet. So negative 16t squared. My initial velocity is 5 feet per second. So it's going to be plus 5t. And the reason why it's plus is because we're assuming that this guy, when he's jumping, is jumping up into the air, okay, as opposed to like straight down diving, okay? If you were just straight down diving, then we would make it a negative 5 because your initial velocity is going in a downward direction. But I'm kind of assuming here that you're jumping up a little bit before coming back down. So that's why it's a positive 5. All right, and then it's plus my initial height, which is 92 feet. All right, so there's my equation. So now what I need to do is I need to actually solve this. So what I'm looking for, again, is I'm looking for this x-intercept right here. So if I'm looking for this x-intercept, right, then I want to find the time when the height is 0. Okay, we want to know when is he going to hit the water? Well, that's going to happen at a height of 0. So what I'm going to do is I'm going to plug in 0 here for my height, right? And then my equation is going to be 0 equals negative 16t squared plus 5t plus 92. Okay, and then that's what we're going to solve. Right now, like I said, we're not actually going to solve this here, but from here, you've got two options for how you could solve this. Option one is you could use the quadratic formula, right? Which is totally an option because that method always works, right? I'm kind of looking at this and I'm saying, well, solving this by factoring, this thing, I don't think it's going to factor. Most of these don't factor nicely. So that's not a great option. We could solve it by graphing. So we could use our calculator to graph. So that's an option. Solving by completing the square, probably not going to work, right? I'm going to have to divide by negative 16 and then take it. That's going to be gross, right? And then solving by square rooting is only when you don't have that middle term. So of our 5 methods, these are the best 2 to use for this particular problem. Okay, so that's how you would solve either one of those. But again, we're not actually going to do that right now. All right, so let's look at the next one. We get a volleyball game. Player spikes the ball over the net when the ball is 10 feet above the court. The ball goes downward at an initial velocity of negative 55 feet per second. So again, that's the difference between hitting up, right? Hitting the ball up in the air versus this. It specifically says they're spiking the ball, which means hitting it straight down. So that's why it's a negative velocity. Okay, so we want to hit the ball back before it touches the court. How long do they have to hit the ball? Okay, so let's start by setting up our equation. So my equation here, again, it's a height function of time. So it's going to be h of t equals negative 16t squared, because we're still talking feet. My initial velocity, they told me was negative 55, so it'll be minus 55t. And the ball is starting 10 feet above the court, so plus 10 is my initial height. Okay, and we want to know how much time. So again, that's going to be the x coordinate that we're looking for. Do they have before it hits the court, right? And when it hits the court, that's going to be at a height of 0. So again, I'm plugging in a height of 0, right? And I'm going to have 0 equals negative 16t squared minus 55t plus 10. Okay, and that's what I'm going to solve. You'll notice this one looks an awful lot like the last one, right? So in terms of how we could solve it, your two best options are going to be either the quadratic formula or using your calculator to graph. Okay, great. All right, so the next one we've got for a particular range of time, the amount in billions of dollars spent on long distance phone calls, right? Because that was the thing that you actually used to get charged for, charged you extra money if it was a long distance call versus a local call, right? Could be modeled by this equation. T is the number of years since 1989. We're going to come back to that. That's important. We want to know, in what year did you reach $60 billion? Okay, so what this is telling me is that $60 billion, A is the amount in billions of dollars, right? So this is going to be an A amount. Okay, so I'm going to take this number and I'm going to plug it in. And since it specifies that A is in billions of dollars, I'm just going to plug in 60. I'm not plugging in the number 60 billion. Okay, so you got to make sure you pay attention to that. So I'm going to plug this into my equation and I'm going to get 60, right, and then equals the rest of this equation. So 0.56 t squared plus 0.488 t plus 49. All right, and then that's the equation that I need to solve. So when we go to actually solve this, you're going to have kind of two options. Okay, so option number one, okay, is that you could get this equal to 0, right? So I could subtract the 60 from both sides. So option one is get it equal to 0, which in this case means subtract the 60 from both sides. So to be 0 equals whatever. Okay, and then once you can do that, you can either do the quadratic formula or use your graphing calculator, right? So you could do either one of those, just like we did in the last one. So that's option one, okay? But option two would be if you took this and you're going to plug it into your equation as two separate equations. So what I would do is I would go into my calculator and go into y equals, right? And again, I'm not going to do the whole thing, but I would type that 0.56x squared, blah, 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 blah up here, right? So plus 0.488x and then plus 49. And then on the other equation, I would type in the second half. So see how I did two separate equations, one for each half of my problem? Okay, and then graph that and find the intersection point. Okay, so that is your other option. So option two would be to put each half into y1 and y2 and then find the intersection. Okay, so that is your other option there. You can do it either way. So, all right. Now, one last thing to mention here is that you need to pay attention to what they define your variable as. So when they tell you that t is the time since 1989, okay, so say we solve this problem and we get 10 is our answer, Okay, so if you get 10 as your answer for t, you then just have to go back and say, well, if t is the number of years since 1989 and I got 10 as my answer, well, then that would be the year 1999. Okay, so that's kind of what you're going to look for with these ones. Right, other quick side note on this problem because it's worth talking about. This is an example of why when you're talking about modeling something, you always do it over a limited amount of time. Okay, so this information was taken from this span of years, which was quite a while ago, right? This is well over 20 years ago. Okay, so when you look at how this equation is modeled, you could use this equation to make a prediction for how much is being spent now on long distance phone calls. And obviously, that would be very wrong, right? If you think about it for a minute, this equation is going to model and it's going to give you an answer for the year 2020, but like no one gets charged for long distance calls anymore. That's not a thing, right? Calls are like the free part of your plan. Okay, so this is just an example of why you always use data to just look at a limited time span, because changes in the world and changes in what's going on can make a big difference on your final predictions. All right, next one. Basketball player passes the ball to a teammate who catches it 11 feet above the court, which is just above the rim of the basket, and then he slam dunks it. The first player releases the ball 5 feet above the court with an initial velocity of 21 feet per second. How long is it in the air before it's caught? Assuming it's caught as it rises. So we'll talk about that in just a second. All right, so let's talk about what's going on here and look at the picture of what this is going to look like. So first off, I can set up my equation. Okay, so my equation is going to be h of t equals negative 16t squared. Right, that's just gravity, that's always there. All right, my velocity, my initial velocity is 21 feet per second, so plus 21t. Okay, and the initial height of the ball was 5 feet. So the initial height was 5 feet when it was thrown. All right, so we've got that part. And then it's telling us that he catches it at 11 feet. So for this one, I don't want to know when the height is 0, right? When the height is 0, that's when it hits the ground, and that's not what we're looking for here. Okay, here, I'm looking for when is it caught at 11 feet. So I'm going to plug in 11 for my final height. And I'm going to make it 11 equals negative 16t squared plus 21t plus 5. Okay, and that's the equation that we're going to solve. Again, you can do it either one of these two methods and you'll get your answer. All right, but then the last thing just to consider on this one. So if you think about what the model of this equation is going to look like, right? If I were to actually draw out like a picture of what this graph looks like. So what's happening is that you've got dude over here, right? And he's tossing the ball and then some other dude is catching it, right? So what's happening with this is that you're going to have this parabola where you're looking for a particular height, and it's going to reach that height in a couple of spots, right? So the question is, where on the parabola is this actually going to hit, right? Like, a second. Okay. So when we talk about, here's the path of the ball and here's 11 feet, right? That 11 feet is going to hit at two separate spots. And the question becomes, is the dude standing here or is the dude standing here? Okay, so that's kind of the judgment call. And that's what they're talking about. As it's caught as it rises. So that's just telling you, well, here's where the ball is still rising up in the air. So this is the spot where it's going to be caught, not this one. Okay, so that's kind of what's happening in that model. All right, great. So this next one, we use 40 feet of fencing to reclose a rectangular garden, and we have the area of the garden. What are its dimensions? So we've played with these before. So we're going to kind of set this up, and let's see. Sorry, I'm choosing the right color. It's a tough job. All right, so 40 feet of fencing, that's my perimeter, right? So I can say that my perimeter 40 is 2 lengths plus 2 widths. And I know the area is 90. This should feel familiar, which is length times width. Okay, so then I can go ahead and solve one of these equations and plug it into the other one, right? So I can figure this guy out, make this 40 minus 2L equals 2W. So then 20 minus L equals W. You could have also solved for L, same deal. Okay, And then I'm going to plug that into this equation over here. And that's going to give me 90 is equal to the length times 20 minus the length, right? All right, and now we've got that set up, and this is where you have some extra options for how you wanted to solve this one. This one would be a good one that you could like simplify and then try to either factor or something, right? Because this part would simplify pretty easily to give you something that might factor or might complete the square nicely. We're gonna have a 20 in for my B term. So that one would complete the square nicely. You could graph it. So you got like a whole bunch of different options. The quadratic formula will always work. You'll have to simplify a little bit first. So you have to get it equal to 0 first, and then quadratic formula. Okay, we could graph it. Okay, we could do a completing the square with this one. I'd be looking for two factors of 90 that add up to 20, and I'm honestly not sure if that exists or not, but I could try factoring it. Okay, so there's a lot of different options that you could take to solve that one. All right, great. This one, all right, so you're going to put in a garden with a pre-existing fence. Okay, you have 40 meters of fencing. You want the garden to be 125 meters square. What are the dimensions? So this one, right, I got a pre-existing fence. So what this is telling me is now I only need this much fencing, right? Because there's a pre-existing fence we're going up against. So my perimeter in this case is going to be just one length and two widths, right? And I have 40 meters of fencing, so 40 equals a length plus two widths. And then my area is still just length times width, so that's 40. Oops, sorry, not 40, 125. My bad, used the wrong number. That was the area. Okay, and then just like the last one, I can go ahead and solve this for L. So this should not be anything too complicated, right? We've basically done these before. The only piece that we're adding in is just how you solve it, okay? So we're solving it in a variety of different ways instead of just the same way that we've been doing, right? And I could simplify this out pretty easily, do a double distributive, or not double, sorry, regular distributive property. Make that negative 2w squared plus 40w equals 125. Right? Bring that 125 over, use a quadratic formula. You could graph it. You could, completing the square to be a little bit messy on this one because when you divide by that negative 2, right, that 125 will end up a fraction, but it wouldn't be bad for completing the square. So you got different options of how you could do that one. All right, next one, we've got a pool here with a 12 by 20 foot dimension. We're going to build a walkway around it. Okay, and then the total area of the pool and walkway is going to be 400. Okay, so what's going on here? So I'm going to try to fit this picture in. But basically, here's the idea, is that we've got a pool that is 12 by 20, right? And then we're saying, okay, well now we're going to add a walkway of uniform width around it. So I'm adding around this a walkway. Okay, and because we know it's uniform width, but we don't know what that width is, I can just say, well, I'm going to call this width X. And it's uniform, so it means that if this is X, then this distance here, come on, pen, is also X, and this distance here is also X, and this distance here is also X. Okay, that's what the uniform part means. Okay, so then we can use that to figure out our situation here. So I'm going off of this area, that the area is 400 square feet. Okay, I don't have anything about a perimeter going around this. There's no like fence that we're putting around. We're just talking area. So I only need the one equation here. Okay, so I know area is length times width, and we're talking the area of the whole thing. So the whole thing is going to be 400. Well, the length of my pool, it was 20, right? But now I'm adding on this width of X on both sides. So my new length is 20 plus 2 X's, right? So my new length is 20 plus 2 X's. And my width, well, that used to be 12, but now I'm adding an X on each side, right? For this walkway. So my new width is 12 plus 2 X's. Okay, and then that is the equation that we're going to solve. All right, so again, you've got some options for how to solve this. You could do your quadratic formula. You'd have to simplify it out. You could throw this in your graphing calculator. This one would be pretty easy to get into intercept form. Oh, no, it wouldn't. I lied, never mind. But you've got some different options for how you could do this one. I take back the intercept form thing. All right, next guy, we got the sum of the legs in the right triangle is 15 inches. The hypotenuse is 12. Find the length of the legs. So this requires you to remember some stuff about right triangles, right? So here's what's going on here. Here's my right triangle. The hypotenuse is 12, which remember is always the long side opposite the right angle. All right, and then we've got two other legs. The sum of the two legs is 15 inches. So if I call this one down here x, that means that this side has to be 15 minus x, right? So that when you add them together, you get 15. So however much you use here, 15 minus that much is how long the other side is. All right, so we've got those dimensions, and now we want to find the length of the legs. Well, now I've got three sides in a right triangle. That's Pythagorean theorem, right? So the Pythagorean theorem says that the sum of the squares of the two legs is equal to the square of the hypotenuse, right? And there's my equation. We could clean this up a little bit, do some double distributive properties, neaten it up a little bit, and make that pretty easy to solve with the quadratic formula. It'll probably factor, might not factor, I don't know. You have to look at it once you simplify it to kind of make that judgment call, right? But you can also just grab your graphing calculator. All right, and then the last one leg of a right triangle is 3.2 centimeters longer than the other. We've got the area of the triangle. We want to find the length of the legs. Okay, so if I'm thinking about what my picture looks like, okay, we know that one leg is 3.2 longer than the other. So if this is x, this one is x plus 3.2. So 3.2 longer than the other one. And then we know the area of a right triangle is 1/2 base times height. So my area of 46.3 is going to equal 1/2 times the base, which is x plus 3.2, times the height, which is x. Okay, and there's my equation. And again, you can clean that up, take a look at it, and then solve that from there. Okay, so that is just a whole bunch of word problems and kind of how you set them up. Again, we didn't want to focus on the solving because we've already focused on solving. Okay, so the point of today was focusing on just setting up these word problems and making sure that we're okay with what we're looking for. Okay, always make sure that you just take that minute and really figure out what am I looking for when I do these problems.